Hello student, let us continue with electronics paper 2, that is digital electronics. Student, let us continue with the second topic, that is logic gates. We have seen first session, second session, today we are going to see the third session. Let us very fast revise the topics covered in session 1 and session 2. In first session we have seen what is meant by logic gate, what is types of logic gate, that is basic gates and derived gates in detail. Then we have seen De Morgan's theorem, first theorem, second theorem along with its proof and how to apply, that is by using De Morgan's theorem how to solve a Boolean equation. So let us proceed. Today we are going to see NAND gate as a universal building blocks. NAND and NOR gates are termed as universal gates as we can construct any gate using NAND or NOR gate. This helps in reducing the cost and the size of the device. So first we will say by using only NAND how to construct the basic gate, that is NOR gate, AND gate and OR gate. Now let us construct a NOT gate using a NAND gate. A NOT gate, recall, NOT gate has a single input and a output is always complement of the input. Always complement of the input. Let us look at the truth table of a NAND gate. Here, when both the inputs are low, the output is high. 0 into 0, 0, 0 bar, that is 1. Again, when both the inputs are high, the output is low. That is 1 into 1, 1 bar, that is 0. Now, this is important for us. See, when both the inputs are 0, we get a 1. Not get maybe SI. When you apply a 0, we get 1. When we apply 1, we get the 0. So when in a NAND gate, when both the inputs are at the same logic state, we get a inverted output. So what we are going to do? NAND gate, we are going to short both the inputs to 1. So now it becomes one input, that is A. So what we got? A bar. So we have converted NAND gate into a NOT gate. So what is the truth table of a NOT gate? A 0. So we apply here 0, 0 bar 1. When we apply 1, that is 0. Hence a NOT gate can be constructed using a single AND gate. So a single input NAND gate performs the same function as the NOT gate. So by using only one NAND gate, we have constructed a NOT gate. Now we'll be constructing AND gate using NAND gates. So let us, what is a Boolean equation of an AND gate? A and B. What is a Boolean equation for NAND gate? A and B bar, the whole bar. So AND gate and NAND gate are complement of each other, right? So here a NAND gate is taken having two inputs A and B. The output is A, B bar. The output of this gate is A and B bar. To complement A and B bar, so we want to remove this complement. So again we will take the complement of this, that is A and B bar. So to complement A and B bar, we connect a single input NAND gate. We have seen how we got the NOT gate from NAND gate, where we have shorted the two input and the NAND was converted into a single input, so it worked as a NOT gate. So here also we want a NAND as a NOT. So here we are connected the inputs. Now A and B bar and bar, double bar. The two complements, that is the first inverts and the second reverts. So the complement disappear. So what we got? We got A and B. The Boolean expression A and B, this gives a AND gate. Using the two NAND gates, we obtained a AND gate. Construct OR gate using NAND gate. It is little bit tedious, because NAND gate Boolean equation is A and B bar, and that of the OR gate is A or B. So now let us see how we can convert the NAND gate to get an output of a OR gate. So here NAND gate is A and B bar. So using De Morgan's second theorem, we can simplify, break the bar, so we get A bar, the operator sign changes to OR and B bar. So first we'll implement A bar and B bar. So for to implement A bar and B bar, we are using a single ANDed AND gate. So A, both the inputs are short together and we apply A. So output will be A bar. Similarly, B, we again apply, use a single ended AND gate, we get a B bar. Now A bar and B bar is applied to a third NAND gate as an input. So what are the input to the third AND gate? A bar and B bar. What is the output? Y is equals to A bar or and B bar the whole bar. Now is this equal to a OR gate expression? Let us see how we can simplify and how we can get this equation equals to A or B, that is the expression for the OR gate. A bar B bar whole bar. So here we'll apply the De Morgan's second theorem. So we'll break the bar. So A double complement, operator sign change from AND to OR, and B double complement. The complement cancels each other or they disappear. This complement inverts and this reverts. So they get the complement disappear. So we got A or B. So by using three NAND gates, we have constructed a OR gate. So using three NAND gates, we have got a OR gate. Now by using the second derived gate, that is NOT gate, let us see how we can construct a NOT gate, OR gate and AND gate. See student, when I was doing construction of NAND gate, first I have constructed NOT gate, then I have constructed AND gate, and then I have constructed the OR gate. But in this gate, I'll first construct NOT gate, then I will construct OR gate, and then I will construct AND gate. Let us see how to construct a NOT gate using a NOR gate. Let's recap the truth table for a NOR gate. NOR gate produces inverted output for conditions when A and B are 0, 0, that is 1, and when the inputs are 1, 1, that is 0. Hence, both the inputs are at the same logic state, then the output is inverted when both A and B are at 0, 0, or when both the inputs are 1, 1, the output we get as a inverted. Yes or no? 0, 0 we got 1, 1, 1 is 0. So we will short the two inputs of the NOR gate. When the input is at logic 0, the output is 0 bar, that is 1, and vice versa. This is NOT gate constructed using a single NOR gate. So by using a single NOR gate, we have constructed a NOT gate. Second gate we would construct is OR gate from a NOR gate. The Boolean expression for a NOR gate is A or B bar. That of OR gate is A or B. This is simple. If we complement the output of the NOR gate, we will get the OR gate. So let us see. So here we have taken a NOR gate. The input are A and B. So the output is A or B bar. So again this is connected as an input to a single ended NOR gate. So what is the input to the second gate? That is A or B bar. So when it is we get the output A or B bar bar. So these two complements get cancelled off. So we got A or B. So by using two NOR gates, we have constructed OR gate. Thus, by using two NOR gates, we got the OR gate. We We'll be constructing AND gate using a NOR gate. So the Boolean expression for the NOR gate is A or B bar, and that of the AND gate is A into B. So let us see how we convert A or B bar to A into B. So here A or B bar, so we take A complement, B complement, and then again pass it through a gate complement. So this complements by using De Morgan's first law. The complement, we break the bar, so it becomes A complement, B complement. The complement get cancelled and we get A to B. So here by using De Morgan's theorem we have simplified the equation. So A bar, B bar. So we got by using a single-ended NOR gate to get to the complement of A bar and B bar, and this we are given to a third NOR gate as input. So input are A bar, B bar. So what will be the output? Y is equals to A bar or B bar, the whole bar. So by applying the De Morgan's theorem, we got A bar bar, the operator sign changes, that is OR bar, that is and B bar bar. Thus the complement, two complements get cancelled out and we get A and B. So by using three NOR gates, we got the AND gate. So we can construct a AND gate by using a three NOR gates. Let's see the binary addition of 2 bits. So 0 plus 0, 0, 0 plus 1, 1, 1 plus 0 is 1, 1 plus 1, the sum is 0 and carry is 1. In binary number system, there are only two digits, 0 and 1. So when you add 1 plus 1, the sum is 0 but carry is 1. When we do addition of 3 bits, that is 1, 1, 1, we get the sum is equals to 1 and carry is also 1. See, 1 plus 1 we got sum 0, carry 1. Add 1, 0 plus 1, 1 and carry 1. So when we add 3 ones, 1 plus 1 plus 1, the sum is 1 and carry is 1. Adders are basic building blocks of any digital electronics devices. Now you can use them to make calculator. Adder circuits makes arithmetic and logical circuits called ALU to perform binary addition operation of data. Adder are of different types starting from half adder. Let us understand half adder. The half adder circuit is useful when you want to add one bit of numbers. We all know by now one bit take value 0 or 1. Half adder is a logic circuit that adds two binary digits at a time. In half adder there are two inputs A and B with two outputs sum and carry. Let us refer to the classic truth table we all use when the two variables A and B are of one bit each. So we know the two variables. So how many combinations? Four combinations, 0, 0, 0, 1, 1, 0 and 1, 1. Here, the sum indicates the value obtained upon the addition, and carry indicates whether there is a carry generated during the addition. Now let us add them. 0 plus 0, sum is 0 with of course no carry. 0 plus 1, sum is 1 with no carry. 1 plus 0, sum is 1, again no carry. Well, however, 1 plus 1 we have seen in binary system the sum is 0 and there is a carry of 1. If the number of terms added are odd, here 0, 1 and 1, 0 odd terms, the sum is 1. Or for even numbers of zeros and ones, the sum is 0. Let us analyze the truth table for sum. Now see the truth table. What is the sum? Truth table 0, 1, 1, 0, where the variable a and b are both are different, the sum is 1. When both the variables are at same value, the sum is 0. This is the truth table for which gate we have seen XOR gate. When the inputs are different, the output is high. Now let us connect this to a XOR gate. Similarly, let us see now the carry. Analyze the truth table for the carry section. This is a truth table for a AND gate 0, 0, 1. When both the inputs are high, then only the output is high. That gives us the AND gate. So sum will be represented by XOR gate and carry will be represented by AND gate. So let us see the logic circuit. Here A and B are the two inputs. They are given to the AND gate. So we obtain the carry as A and B, and the same inputs A and B are given to the XOR gate. So we obtain the sum as A XOR B. Let us see. This is a half adder logic diagram. So by using the half adder circuit, let's see the proof. So we are going to add 0, 0. The sum is equals to A XOR B, 0 XOR 0. Both the inputs are same, so output is 0. That is sum is equals to 0. Carry is equals to 0 into 0 using AND gate. So 0, 0, 0. The case 2, when A equals to 0 and B is equals to 1, so we are adding 0 and 1. So sum is again equals to 1 because odd number of inputs and carry is equals to 0. Third case, again sum is equals to 1, the input is equals to 1 and B equals to 0. Sum is equals to 1 XOR B. Again the inputs are different, so sum is equals to 1 and carry is equals to 0. Last case 1 plus 1. So sum is equal to A XOR B. Both the inputs are same digit, so the sum is 0 and carry is 1. So let us see the symbol of half adder. So here two inputs and two outputs, sum and carry.
Now let us see the next adder circuit, that is full adder. Full adder can add three binary digits at the time. It is actually the extension of half adder circuit. It has three input A, B and C and two output carry and sum. So let us analyze with the help of the truth table. Now three inputs A, B and C. So how many combinations of zeros and 1? 8 combinations of zeros and ones. So first 0, 0, 0. So we are adding the 3 bits. So 0 plus 0 plus 0. The sum is 0. So there will be obviously no carry. When we have one input, any one input is high, means odd number of inputs are high, the sum is equals to 1. See, 0, 0, 1, odd number of input is high, sum is high. 0, 1, 0, again one input, again odd number of inputs, so sum is high. Again here 1, 0, 0, then sum is 1. And when odd number 1, 1, 1, that is 3 input in 1, 1 hai, the output is sum is equals to 1. Carry is 1 when two or more inputs are high. So here two inputs are high, so carry is 1. Here again two inputs are high, 1, 0, 1, that is 1. Here again two inputs, so 1 plus 1, sum is 0, carry is 1. 1 plus 1 plus 1, sum is 1 and carry is 1. From this we can get the equation for a full adder. So what is the sum equation? Sum is equals to A XOR B XOR C and carry is AB plus BC and AC. If you analyze the truth table, you will get this equation for sum and carry. Now let us draw the logic diagram for full adder. So here we have got A XOR B. So using a XOR gate, A XOR B. The output of this first XOR gate is A XOR B, and we are giving the third input C in as the third input. So A XOR B and C. So what is the sum? A XOR B XOR C. Now let us see carry. We want AB, BC and so AB. So how will connect AB? AND gate. BC again are combined with AND gate, and AC with AND gate, and these three are combined with a OR gate. So here this AND gate is giving me A and C. So output of this AND gate is AC. Second AND gate, it is C and B. So it is giving me BC, and third AND gate is giving me A and B. So I got here AC, BC and AB. So and these are given to which gate? 3 input OR gate. So my carry is AB plus BC plus AC. Let us see the symbol for a full adder. So here two inputs AB and the third input C in. We have a sum and we have a carry. Student, let us see the difference between inclusive OR and exclusive OR. So sometimes they may ask for 3 marks question or 4 marks. Distinguish between or compare inclusive OR and exclusive OR. Now inclusive OR gate is a basic gate and exclusive OR gate is a derived gate. Now definition, logic statement: if A is true or B is true or both are true, then Y is true. If A is true or both B is true but not both, then Y is true. So let us see symbol. So here we have seen the symbol of a OR gate, and this is a symbol for XOR gate. Truth table 0 0 0 0 1 1 1 0 1 and 1 1 1. Truth table for exclusive OR. AB inputs are 0 0, output is 0. When the inputs are 0 1, output is 1. 1 1 0 1 and 1 1 0. The Boolean equation for OR gate is Y is equals to A or B, and Boolean equation for XOR gate is Y exclusive or B.
Let us see the example of XOR gate. XOR gate as a parity checker. So in exam they may ask to define XOR gate and explain XOR gate as parity checker. What is a parity? Parity is a bit in form of 0 or 1 used to detect the error in the signal. It only detects a single bit error, not more than that. Parity is used in data communication. When we send the data in binary digit, the parity used to detect the error. So when we send the data, along with that additional bit is sent. At the receiver end, it is being checked if the data received is correct or not. If not, means there is error in the data. So a group of bits or word can have even parity or odd parity. So there are two types of parity, even parity and odd parity. Let us understand odd parity. Odd parity means odd number of ones. If a word or bits, a group of bits has number of ones odd, then it is called as odd parity. Like here, see the word is given. So how many number of ones are there? 1, 2, 3, 4, 5, 6 and 7. 7 number of ones, so we as a odd parity. Here the even parity means even number of ones. So let us see 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So it is an even parity. Let us construct a 4-bit parity checker using XOR gate. XOR gate recognizes the word with an odd number of ones. Therefore, the XOR gate is ideal for testing the parity of the word. So XOR gate is ideal as per the definition. A 4-bit parity checker can be constructed using XOR gate. Three input the word, that is A0, A1, A2, A3 and the Y output. Even parity word produces low output. If the parity is even, it produces a low output, and a odd parity word produces a high output.
Now let us see the truth table for 4-bit parity checker. So here we have a 4-bit A3, A2, A1 and A0, the word, the number of ones in the input, the Y output and parity, either even parity or odd parity. Now here number of ones is 0. The word doesn't contain any 1 in this. So number of ones at the input is 0. So output is 0. So what type of parity it is? Even parity. Now let us check this. So 0, 0, 1, 1. Number of ones at the input are 2. So the output is 0 because even parity. When the number of ones are even, then the output is low. When the number of inputs are odd, the output is high. Now in this case, see here 0, 1, 1, 1. Number of one inputs is 3. So it is output is high, that is odd parity. So this way we see what is a even parity and odd parity 4-bit parity checker. Student, let us summarize what we have seen in today's session. So first we have seen NAND and NOR as universal gate, then how to construct the basic gate using NAND and NOR only. Then we have seen half adder circuit. There are two adder circuit we have seen, half adder and full adder to add 2 bit and 3 bits. Then we have seen the application of XOR gate, that is XOR gate as a parity checker. So we came to the end of the logic gate session 3. Thank you.